what I will talk about today is a physical model of the rate, state, and temperature dependence of friction, particularly looking at how we can incorporate the effect of multiple competing healing mechanisms and how these affect the effective frictional properties. And this is important to understand the depth of the seismogenic zone, the frictional properties of faults, and eventually how they affect seismic cycles, the style of ruptures, whether they are crack-like, pulse-like, super shear, the recurrence time. So it's fundamental aspects of friction that shape a lot of aspects of earthquake physics and seismic hazards. And I'm going to spend maybe 20 minutes summarizing some very important work that was instrumental to shaping these models, constraining the models. And then the second half of the talk describing how the model is built, basically describing a few tractable assumptions that will explain many of the data that I will introduce first. So I will start with the simplest and most robust observations about friction that have been summarized by this review paper of Byerly in 1978 that show that many different types of rocks of all sorts of origin, sedimentary, igneous, metamorphic, end up having the same coefficient of friction. And that is quite surprising at first glance, because if you take the weakest rocks or the strongest, if you take very weak sedimentary rocks or very strong igneous rocks, they end up having the same friction coefficient, even though they have many different properties otherwise. So they can all be described by a friction coefficient that varies between 0.6 and 0.8 at relatively high normal stress. So that's kind of a very fundamental aspect of friction, that it's relatively independent of rock characteristics at first order. Another aspect that is fundamental to earthquake physics is that friction is actually time dependent. And that's important because without this effect, there will not be seismic cycles. And the frictional resistance to sliding of faults drops during earthquakes, but then after the earthquake has happened, for the decades that make the interseismic period, fault and friction recovers over time. We call this healing or strength recovery. And that seems at first order to be linearly proportional to the logarithm of time. So the initial recovery is extremely fast, but then it takes many, decades to heal furthermore. So there is this so-called logarithmic aging of friction that was identified by Dietrich and then others in the 70s. That's a fundamental aspect of friction that models need to incorporate. But going beyond static friction, what has been firmly established in the following few decades is that friction is not only dependent on the rate of sliding, the velocity of sliding, but also the history of deformation. So it makes things much more complex. And the history of deformation, of past deformation, seems to be captured by so-called state variable of the system that can be described in these experiments. These are velocity step experiments. And when you force two solids to slide past each other at a fixed velocity, at an imposed velocity, you can monitor the frictional resistance. And when the velocity of sliding increases abruptly, there's a direct effect of an increased resistance. But over time, there's an evolutionary phase where the friction evolves, continues to evolve to a new steady state. And so there is a rate dependence of friction, but there's also a state dependence of friction. And these are fundamental aspects that allow seismic cycles. So the question remains, what is the state variable? What does it mean? Can we measure it? And for many decades, actually, this has been relatively elusive, but there's been some fundamental laboratory observations by Dietrich and Kilgore in the 90s that have shown quite convincingly, in my opinion, that the state variable is actually the size of the micro-asperities that bear the true load at the contact. And what these experiments have revealed is that solid contacts, natural surfaces are very rough, and only a very small fraction of the contact is in actual contact with the other side. This is of the order of a few percent. And so it's quite fundamentally important, because that means that these micro-asperities, another name for them is contact junctions, are experiencing a very large load, a much larger stress than the overall contact. And so that forces them to deform faster and perhaps in plastic ways. And so these experiments have shown that these asperities change in size if you force them under different loads, and that's what these experiments are. So you see under 2, 5, 10, and 20 megapascals how these asperities look wider. So it seems that so that taking into account these micro-asperities is fundamental to friction. I need to mention that these experiments are only possible with transparent materials, and these experiments are done by shining light through this frictional contact and looking at how much light is reflected or transmitted. So when there is a contact, light is transmitted. When there's no contact, it's mostly reflected. And so that allows these experimentalists to quantify the amount of contact at any time. And these experiments were conducted on plastic, PMMA, for example, but also on real rocks, such as quartz and calcite. So this seems to apply to a wide range of materials. But second, the same authors showed that these micro-asperities grow over time in stationary contact. So if you leave two solids under normal stress at stationary contact, the micro-asperities will start growing over time. Another name for this is flattening, because of course they grow by collapsing, and so it increases the area of contact. This image shows you spatial distribution of these contact junctions at 1 second, 100 seconds, 10,000 seconds. So you can see that there is logarithmic expansion of this, the size of these asperities. So these experiments show that the area of contact is likely to be a state variable for the system. In addition, they ran these experiments, they forced these contacts that impose velocities, 1 micrometer per second, 0.1, 1, 0.1. And what they see is that the so-called real area of contact, so the area of these micro-asperities, seem to reach a steady state that depends on velocity. So these contacts depend on normal stress, they depend on time, they depend on sliding velocity. So all of these experiments seem to imply that the area of contact is the state variable, or a state variable for rate and state dependent friction. So this was in the 90s. Then in the 21st century, and now going on for 2 decades, there's been other experiments on transparent materials that not only image the real area of contact, but manage to image its evolution during the passage of seismic ruptures. And so that's simply a technological improvement that allows the imaging of this area of contact at the frequencies of megahertz, right? So enough to look at the evolution of the contact area within microseconds. So these experiments are done in the laboratory of Jay Finberg in Israel, and they have allowed a wide range of important discoveries described in many papers in the last 20 years. Some of them are cited in this slide. And a typical result looked like this figure, where you have the distance along the interface of transparent material, and the y-axis is time, and you can see in color the evolution of the contact area. In reality, this is not the contact area. The true measurement is the intensity of light that is transmitted. But the fundamental assumption here is that light is proportional to the area of contact. And I think that's a reasonable assumption. So you can see how the evolution of the real area of contact through the light evolves over time, and it drops from a high value to a low value with the passage of the seismic rupture, which in this case goes at the Rayleigh speed. So this is a very important experiments that confirm once again that the real area of contact is a good candidate as a state variable. Okay, so now we change gear and we look at other aspects of friction. And one of the most important experiments of the 90s was also one of these very important experiments was performed by Frederick Chester and some of his collaborators that really demonstrated that friction is a thermally activated process. So he conducted, I think it's very well explained in this figure from his 1994 paper, that shows velocity step experiments that demonstrate the rate and state dependence of friction. So in the first few steps here, he imposed sliding at various velocities. And you can see the direct effect and evolutionary phase that follows. These are well-known effects. But then, at some point, he maintains the velocity of sliding constant, and he changes the temperature of the sample. It's simply by heating it up very quickly and maintaining this temperature for some time. And what these experiments show is that you also have a direct effect and then an evolutionary phase, and it looks almost identical to a change of velocity. So changing temperature or changing velocities have equal and opposite effects. The reason is that for an increase in velocity, there is an immediate frictional drop followed by a recovery. Whereas for the velocity, if you increase velocity, there's a frictional increase and followed by a recovery. So this is why I mean equal and opposite. One leads to weakening, the other leads to strengthening. But otherwise, they look exactly the same. So it really demonstrates that friction is thermally activated. Well, now we have much more experiments and contributors, but there's a wealth of laboratory experiments that continue to explore the temperature dependence of friction. And some of them you will recognize. Perhaps some of the experimentalists are in the room right now. And many were conducted by Professor Fay and collaborators. And so going back to this thermal activation, in the 90s as well, there was some physical models that were derived to explain the temperature dependence of friction. And a fundamental prediction of these models was to predict that the velocity dependence parameter was linearly dependent on the absolute temperature in Kelvin. So at 0 Kelvin, there should not be any velocity dependence. And at finite temperature, the velocity dependence parameter will increase. And if you double the temperature, you double the velocity dependence parameter. And this theory explains the logarithmic formulation of the empirical rate and state-dependent friction and makes that prediction. Well, there's two issues with these models. First, the logarithmic dependence of velocity is problematic. And maybe you have noticed that before if you thought about this formulation, that if you impose a zero slip velocity, well, it predicts an infinite frictional resistance, which is unrealistic. So there's a problem with this formulation in the first place. And second, many of the experiments that have been done in the last 2 decades show that the velocity dependence parameter is roughly independent of temperature. And this is illustrated in these examples, in this figure, that show the velocity dependence parameter for the direct effect. It's called A. I will define it later. And it is called A minus B at steady state. And so the velocity dependence is shown in white here for the direct effect. And you can see that it's roughly independent of temperature for many hundreds of degrees. Okay, sometimes it's even decreasing with temperature. So it's firmly invalidating the theoretical models of thermal activation that were proposed in the 90s. What these experiments show otherwise is still a thermal dependence, but not expressed for the parameter A, but for the parameter A minus B, which means that essentially B is a function of temperature. And that's shown with this red line. And it's a typical result that we see in many, many experiments with velocity strengthening, so a frictional parameter that is positive at low temperature, and velocity weakening at high temperature. So, and that's kind of an interesting result because it predicts that in the shallow crust, there would not be frictional instabilities, there wouldn't be earthquakes, and at higher temperature, that's where earthquakes will nucleate. And so it basically helps us understand the depth of the seismogenic zone. Also, this so-called shallow slip deficit. Even if earthquakes rupture the entire crust, there will be more slip at great depth than at shallow depth. And so it also helps us understand this. And so it's important for seismic hazard, for example. I'm going to stop here for a second. Can everybody hear me well? Because I don't have any echo on my end. Lifeng, can you hear me?
Yes.
Okay.
Yes, it's very clear.
Okay, thank you. I was just confirming. So basically, we start to have a good picture of how friction works, with some exceptions that we can perhaps discuss later. The direct effect parameter is independent of temperature. The steady state parameter is very sensitive to temperature, and that has a lot of important implications. And so these are the type of data that can help us constrain a physical model of friction that will be slightly different from what has been presented before. And before I go into these details, I want to describe some other very important experiments that indicate that there is a very different behavior at so-called intermediate slip velocity and slower, and high slip velocity. And there's a strong weakening of friction, so that a strong reduction of friction at high sliding velocity. That's been documented in many different experiments. And these are summarized here with a review paper from Geology some 10 years ago now. And that shows you that you basically very quickly evolve from a normal barely friction at intermediate sliding velocity to close to zero at high slip velocity. So to me, that the physics at high slip velocity and intermediate velocity is very different. At intermediate velocity, so up to a millimeter per second, to all the way to static, this is friction, and it's relatively simple. And at high slip velocity, I call this lubrication, for lack of a better word. But the reality is many different mechanisms of weakening, including partial or full-on melting, including the formation of silica gel, the thermal decomposition of clay minerals, so chemical reactions that are thermally activated, the coating of grains by nanoparticles that lubricate the contact. So a lot of different physics. And so you can't model this lubrication domain and the frictional domain with the same physics. And so for the rest of this talk, I'm only going to talk about friction, so the intermediate sliding velocity all the way to stationary contact. And I will leave the lubrication part for a later presentation because it's basically a different subject. If you have any question or comment, now is a good time, and because I'm going to start the next part of the talk.
Yes. Yeah, I'm trying to ask anyone have a question to Sivan.
I haven't introduced any new material yet, but yeah, I'm going to start now.
Okay.
Okay. So basically, I'm going to introduce basically three assumptions, physical assumptions, that will lead us to a mathematical formulation of a model that can explain all of the observations that I've presented so far, except the lubrication, which requires different assumptions. So how do we do this? We start with the realization that a frictional contact is borne by these micro-asperities, and this is these micro-asperities emerge because of the roughness of the contact, and so only a small fraction of the interface is in true contact. And the physics of friction, starts from that. This is called adhesion theory. It was introduced by Bowden and Tabor in the 60s. So it's fairly well accepted, actually. But the implications of that can vary based on further assumptions. But if the contact is rough and the forces are supported by micro-asperities, then in principle, the theories that describe these simple contacts should apply. And the simplest of which is the theory by Hertz, which he derived in the 19th century. And it's basically an elastic solution that describes the size of the contact, so the real area of contact, and the normal stress, subject to, when a spherical bead is subject to a prescribed normal stress. And so this is a closed form solution, and the area of contact scales with the initial radius of curvature of the sphere, which is d in this formulation, and it scales with this normal stress applied to the bead to the power of 2/3. So essentially, the Hertzian contact, as ideal and simple as it is, cannot explain friction because it has this immediate dependence on the size of asperities and a power law relationship with normal stress. So this does not work, and so that leads to this paradox. But that was resolved in the mid 20th century by introducing roughness to these contacts. And so there are two n-member models for this roughness. And the first one, described by Arshar, the beads themselves have a fractal topography. So there's a large scale radius of curvature, and then the contact is rough, and even the contacts themselves start to have a higher level of roughness, and this goes forever, essentially. And so if the beads themselves are rough, there is a closed form solution for the area of contact, and it happens to be almost linear with normal stress. So it's normal stress to the 26th, 27th, or almost 1. And it has a very weak sensitivity to the large size of this bead. So the sensitivity is d to the 1/9, right? So that's the first model. Another model is assuming a long wavelength topography of the contact. So all the beads are identical. They have this radius d, but they start from different heights, which follows the overall, roughness, large wavelength of the surface. And so this is, and the height is basically random. So they basically touch the other side starting from different heights, which is randomly distributed. And so we can look at the average area of contact, the expected value in a statistical sense. And that also becomes exactly linear with normal stress. Like Bayer's friction law, right? And has also weak sensitivity to the size of these beads. So now it's square root of d. So in reality, fault friction is much more complicated than these n numbers. First, it's not just the contact between one side and the other. It can involve a gouge layer with many different beads and many contacts. The grains may not be spherical. They can be angular. They have different sizes, different shapes. A lot of fundamental differences with these simple models. So what we're going to do next is take the spirit of these results, where you have a linear relationship with normal stress or approximately linear, and a weak sensitivity to the size of asperities, and make it a little bit more general. But we keep the sensitivity to the size of asperities because we saw in the experiments of Dietrich and Kilgore that this size evolves over time. So we want to keep it as a parameter. And so that's how this first assumption is implemented in the physical model. We're not at the stage of friction yet. We're simply describing the real area of contact as a function of normal stress and the size of micro-asperities. So given that they're not spherical in nature, the size can be thought of as the local radius of curvature of these asperities around the contact. And so this is formulated in this equation. This capital A here is the contact density. So it's the real area of contact divided by the nominal area. So it's a non-dimensional quantity. Mathematically, it has to vary between 0 and 1. But in practice, it's only of the order of a few percent. Because it's very small, we don't have to worry about a complex function of normal stress. So we then assume that there is a linear relationship with normal stress. So that leads to this numerator with C plus mu naught sigma. That's the linear relationship. In reality, the function of sigma can be arbitrary, it can be f of sigma, but we linearize it by a local Taylor series expansion with a slope and an intercept. And so that's cohesion and the friction coefficient. But this quantity is stress, so it needs to be normalized. And so the normalizing factor is the material hardness, chi. And that represents how difficult it is to flatten these asperities given their mechanical properties. And second, there is a sensitivity to the size of these asperities. So that's captured by the second part of this equation with a function of d to the m over n. And m over n is a very small quantity. It's smaller than 1. And so that means that this sensitivity to size is weak, but it exists. And so we can calibrate this equation to the laboratory data from Dietrich and Kilgore. And that's kind of a very, I don't know, I think it's a very smart experiment, because they basically subjected different materials, different normal stress, and literally image the area of contact. So we can directly use it to calibrate the equation. But in addition to that, they prepared the surfaces with different grit. Grit is a kind of a way to control the roughness of the surface. And the higher the grit, the finer the grains on the surface. So it eliminates the large grains, essentially. And so these experiments essentially control the grain size. And so you can basically assume that the size of the contact junction is inversely proportional to the grit number. And so what we see in these experiments is that we can explain at first order the linear dependence of normal stress. And you can do that for quartz, glass, calcite, acrylic. And that's, at first order, it's linear with normal stress. But then, as these experiments are carried out with different grit numbers, you can also find slightly different curves for different grits. And so there is a dependence on the size of asperities, but it's a second order dependence. It's not as important as the normal stress. But essentially, we can calibrate this equation with data for stationary contact. The second thing that we need is connect the area of contact to fault strength. Okay, and that's actually the easiest part, but it is an important assumption, and we assume also, following adhesion theory, that the yield strength, the strength that we need to overcome to allow sliding, this yield strength is proportional to the real area of contact. So the larger the area of contact, the more the frictional contact, the frictional resistance, right? And that's this first equation. It's the yield strength, sigma y, is proportional to the area of contact. But this proportionality coefficient is not random. It is the material hardness again. And so that happens to be important. We will see later why. So we have a yield strength, and then we're going to write a flow law that basically describes if you know the stress and the temperature of the contact, you can predict the velocity of sliding. The stress, I should perhaps say that it's basically the amplitude of the shear traction. And that's expressed in this second expression here, with, you see, the velocity is proportional to the stress to a power n times an exponential of a function of temperature. So what does that mean? It means that if the stress is greater than the yield strength, you raise this to a power n, and it's very large. And so the result will be an extraordinarily large number. So the velocity will be very high. So it will slide and break very fast. On the other hand, if the shear stress is lower than this yield strength, you raise that to a power that will give you a number that is much smaller than 1. And so the velocity will be very low. It will basically lock. So that gives you a mechanism to slide and break, or to lock in place. And this is modulated by temperature through an Arrhenius activation law. And so this is very typical in physics. We say that this is thermally activated and depends on an activation energy Q. The variable T naught is a reference temperature. It's associated with entropy, essentially. And so how can we think about that? I like to connect it to a simple static yield criterion. So if you consider a static yield criterion, sigma y, that means that if the stress reaches that number, you fail So velocity can be anything along that line. But if you consider a power law, this is a little more subtle. It says, well, if you approach sigma y, you slip very slowly. And if you exceed sigma y, you slip very fast. And so I show here different slopes for different power exponent n, from n equals 55 to n equals 150. That happens to be the numbers that actually fit the data that I will present later. So these are actually real numbers. And so basically, for the higher the power exponent, the more you approach the static yield criterion. But in reality, to describe the velocity of sliding, these numbers have to be finite. So we have a very, very simple way to predict velocity based on stress and temperature. And the next step is simply to connect the dots. So how do we connect the dots? We have a flow law for velocity as a function of stress and temperature, but the yield strength is proportional to the area of contact. But the area of contact it depends on normal stress, the material hardness, and the size of asperities. So we can substitute these expressions and combine them, and we get the bottom equation, which is a rate, state, and temperature-dependent constitutive relationship for fold slip. And that actually explains the first data set that I showed. It explains the Bailey friction law, actually, because if you notice, the material hardness vanishes from this expression. It is gone. And so it explains why the weakest rocks or the strongest may have the same or similar friction coefficient and no other different properties, because the same property controls the flattening of the area and the yield strength, and it compensates. And so in one expression, it's at the numerator, and in the other, it's at the denominator. So it cancels out. And so that explains in a very simple way why all these rocks would have very similar properties. Okay, and so essentially now we find a constitutive behavior, and it's slightly different from previous expressions in the sense that all the terms multiply each other instead of adding to each other. And the state variable is not something that is just a concept. It is a material property that you can measure. It is the size of micro-asperities. And because the formulation is not, perhaps is new to many, I like to kind of break it down and show you how simple it actually is. Because instead of thinking of velocity as a function of stress, size of asperities, and temperature, you can look at stress as a function of these dynamic variables. So you kind of invert the relationship, and that gives you the equation on the lower left, where stress is basically C plus mu naught sigma times terms that depend on velocity, size, and temperature. And notice that all these three terms, velocity, size of asperities, and temperature, are all raised to the power 1 over n. And I already showed you that this power exponent n must be very large, greater than 50. So when you raise anything to a 1 over n, right? You raise anything to a small power, it converges to unity. So as a kind of an absurdly large example, I raise 1 billion, 10 to the 9, to the power 1 over 60, and that's just 1.4, right? So basically all these terms, since they are raised to the power 1 over n, they look like a small deviation from 1. And because of that, if you ignore them, sometimes you simplify the expression tremendously, and it simplifies to tau equals C plus mu naught sigma. And that's the Coulomb static failure criterion. So it's basically explaining why this works.
Yes, Sivan,
yes,
sorry, can
yes.
you interrupt you? Seems Jianye want discuss something. Chen?
Yes, I do have a little question about the your assumption of the last point about the power of a small equivalent will come to one. Um,
Yeah.
uh, it's true, but it's only for the power law part, but not for the potential portion where you have temperature. When the temperature changes by a few hundred degrees, this last term may changes a lot.
Yeah, you're right. So in reality, this this assumption works not when you consider all the terms one by one, but if you consider all of V, D, and Q over T, and you raise all of that to the power 1 over n, um, then then it works. Um, and well, we can do the math quickly. Basically, R is 10 roughly. Temperature is above 300, and Q is of the order of 100,000, right? And so you get Q over RT of the order of 10 maybe, and then n is greater than 50, so you have a ratio of 10 divided by 50, 1 over 5, and so that combined with the other terms, you can this approximation works, but it's not actually necessary. I'm just mentioning that for the sake of the argument and the relationship with the Coulomb static failure criterion, that it works. But in practice, you are right that temperature is quite important. And if you want the Coulomb static failure, if you want to use the Coulomb failure criterion, you probably would have to use different friction coefficient at different temperature because you can't ignore the temperature effects. So I'm actually agreeing with you. I think that temperature, the effect of temperature is not small sometimes.
Yeah, thanks.
Yeah, thanks for that clarification. But you understand that this claim here is simply for the sake of this one slide, and I'm not making this approximation later on. Okay, so we've looked at two assumptions so far. The first one was the assumption of how the area of contact works. The second was how velocity worked with respect to stress and yield strength. And now to kind of finalize the model, we need to allow the size of these micro-asperities to evolve over time. And so that's perhaps the most interesting part because there's in fact many ways that these contact junctions evolve over time. And I just want to remind you that this evolution is very well imaged in the laboratory, in stationary contact by the experiments of Dietrich and Kilgore, at steady state for imposed sliding velocity by the same authors, and by 2 decades of experiment of J. Finberg and collaborators during dynamic ruptures. But it's otherwise quite difficult to image for non-transparent materials. So there's a little bit of an extrapolation here. But we know that these contact junctions are supporting an extremely high load because they are subject to the same forces than all of the contact, but they are very small size, concentrate the force over a small area, and so that gives rise to a very large stress. So they are subject to a lot of stress, and that makes it possible for them to flow with various different mechanisms. The most universal mechanism of flow for these asperities is what I call viscoelastic collapse. It's simply viscoelastic flow of these asperities. But I add this term collapse because they just close. Okay, so it's fault perpendicular motion. You can also call it viscoelastic flattening. But if you look at this diagram on the upper left, you can see that these asperities are subject to tremendous normal stress. But because of their shape, on the left and right sides, there's very little stress. And so if you look at this system, there's a lot of stress in one direction, very little in the other. That leads to deviatoric stress that it's about plus or minus 45 degrees. And so these asperities, because of normal stress and their shape, experience a lot of deviatoric stress. And that leads to viscoelastic flow. So then there's a lot of individual experiments on viscoelastic flow of different materials. And this is a thermally activated process. It has activation energies between 50 and 700 kilojoules per mole, depending on mechanism. These can be diffusion creep, dislocation glide, grain boundary sliding, etc., that happens inside the asperity or near the surface or at the surface of these micro-asperities. This is a universal mechanism because it can work in dry and wet conditions. Another one is so-called subcritical crack growth. That's kind of a mouthful. So what is this? So it's a crack first. It's a very simple structure. It's kind of a hole in the rock, and there is dislocation across it. But that under relatively low stress, this crack does not fail catastrophically, and instead it lengthens. So the length of the crack increases. Typical numbers are nanometer per second. And that can also happen in dry condition. But then there's many other mechanisms that happen in wet condition. The first one is also subcritical crack growth, but assisted by chemical reactions near the crack tip. Technical term for this is stress corrosion, and it involves the diffusion of species in and out of the fluid that either accelerate or slow down the crack propagation, while the crack lengthening. Another mechanism is crack healing or crack sealing, and it's simply the precipitation of solid within the cracks and the pore space that basically increase the area of contact and cohesion of the material. So this is linked to cementation, and it's also thermally activated because it's linked to the chemistry of precipitation, and that has activation energies between 35 and 80 kilojoules per mole. Another very important one is the so-called pressure solution creep. It's also called dissolution precipitation creep, where the very large stress concentration of these asperities force the dissolution of the solid phase in the fluid. The fluid is assumed to be saturated, and so if you dissolve into this saturated fluid, that leads to the precipitation of ions somewhere else in regions of low stress. And that also has activation energies between 17 and 75 kilojoules per mole. And as you've seen, anytime fluids are involved, the mechanisms have a lower activation energy. And for those who are not familiar with this, for example, a mechanism that has an activation energy of less than 50 kilojoules per mole will be almost instantaneous at room temperature. And if you have an activation energy of 100, it will take days and weeks to happen. So that's kind of the sweet spot. But of course, here we're talking about seismic cycles, so we do have time. We have decades for these processes to manifest themselves. And we're also talking about conditions of the crust, at 500 degrees, for example, 300, 400, not necessarily room temperature. So all of these mechanisms can actually participate in fault zones, in gouge layers, etc., etc. So we have different mechanisms in dry and wet conditions. that can deform these asperities and flatten them. And if they flatten, that increases the area of contact and strengthen the frictional resistance of the whole contact overall. So different mechanisms. The second layer of consideration is that we have heterogeneities, and a gouge is made of a rock, and the rock is made of different minerals. So we have different rock forming minerals. And that's important because even for the same deformation mechanism, we would have different activation energies depending on the mineral. And so I like to take the example of granite because first, it's an important rock type for the continental crust. And it has a typical composition, including some phyllosilicates, mica, feldspar, some quartz. And there's been experiments constraining the activation energy of viscoelastic flow for these individual minerals. And there's also a wide range of activation energies. Phyllosilicates are very weak, they're anisotropic. They have a low activation energy between 28 and 66 kilojoule per mole. Quartz is relatively weak, has activation energy between 135 and 240. And feldspar between 150 and 600. And this wide range is because viscoelastic flow actually has different mechanisms. They're all viscoelastic, but diffusion creep, dislocation creep can have widely different activation energies. So there's more details to that. And so granite, would have, even for the same viscoelastic mechanism, would have different activation energies because of different types of minerals. Calcite, for viscoelastic flow, also has relatively low activation energy, 145 to 150 kilojoule per mole. Pressure solution creep, also it's well documented for quartz and calcite with very low activation energies. And I should have mentioned this subcritical crack growth is also well documented. The activation energy of that is well documented through the review paper of Atkinson in 1984, which documents the activation energy for many different rock types, actually. So there's basically two axes to consider, the mechanisms and the minerals. And so if you consider one or the other or both, that gives you a wide range of activation energies. And so to me, that explains why certain mechanisms are activated at different temperatures, because different mechanisms exist, whether it's dry or wet, and depending on the texture of the gouge. And second, because it involves different minerals. And so you can imagine the micas deforming first, then the quartz, then the feldspar at different temperatures with the same mechanisms. So that motivates the use of different activation energies to explain how these contact junctions flatten over time. And then this can be formulated mathematically with a model, with an evolution law that describes the flattening of these contacts. So it's expressed in a very simple way, where we have an evolution law for the radius of curvature of these contact junctions. And so if this radius of curvature increases, that means the contact is flattening. And if it decreases, that means it's kind of roughening. And so we can express this in two different ways, two different end members. The first one is the aging law end member, because I will show later that this formulation simplifies to the empirical aging law if you make some simplifying assumptions, or to the slip law end member, because it simplifies to the slip law under some simplifying assumptions. So let's consider the aging law first. So first, this formulation describes the rate of change of the radius of curvature of micro-asperities. So it's d dot over d. D dot over d, so it's the rate of change of d divided by d. So that's homogeneous to a strain rate. Basically, the left-hand side is a strain rate. That's kind of interesting. What kind of strain is that? Well, It's the strain of compaction and dilatancy. So it's the strain in the fault perpendicular direction. Because of course, as you flatten, you collapse. And so that changes the thickness, the overall thickness of the gouge layer. So it's a strain in the fault perpendicular direction. And that has a positive term in blue and a negative term in red. The blue terms are for the healing, and whatever they do, they always increase the radius of curvature, because all these terms are positive. And the red term has a minus sign, so it decreases the radius of curvature, and that leads to weakening. So the negative term is simply the contact rejuvenation, and that allows weakening during seismic, during sliding. That's typical. But let's look at the blue term. The blue term is a sum. So you see it's sum from k equals 1 to n. So it's a sum of many terms, an arbitrary number of terms. These terms are mechanisms and or minerals, right? So if you have only one mechanism, say viscoelastic flow, but you have 3 different minerals, you will have to sum from n equals 1 to 3, because that is the viscoelastic flow of micas, quartz, and feldspar, for example. Or it can be different mechanisms for a single mineral. So it's a little bit empirical how this is done, and perhaps some mechanisms dominate over the other, some minerals dominate over the other. So you don't have to sum them all. And inside that sum, you have a term that is 1 over d to the p. And then it multiplies an exponential with an activation energy and a temperature term. So this is also an Arrhenius activation law, right? So there is a activation enthalpy H and the reference temperature Tk. And that's also associated with entropy. And that multiplies a term that has g over d to the p. G is a reference rate of growth. It has units of d to the p per second. And 1 over d is an interesting quantity because it's in the microstructure, the only characteristic size of the system, there's nothing else, is d. So 1 over d gives you a strain and a stress. So you can think of this as a power law of, so 1 over d to the p is sort of a power law of stress. Basically, what we're doing here is summing the strain rates from different components of deformation. And hence, that's why the sum is additive, right? You can, whichever way you deform, the deformation is additive. And so that becomes the evolution law. And since different mechanisms have different activation energies, they may dominate over certain ranges of temperature. So that will allow some transitions in behavior at different temperatures. So that describes the aging law n number. And then for the slip law, the only difference is that instead of having these terms adding each other, in the slip law n number, they multiply each other. So the strain rate is proportional to the log of the product of different terms. In the lab, we see behaviors that support the slip law n number and behaviors that support the aging law n number. So none of these two formulations are valid in all cases. So we consider them as n number just for discussion. The aging law allows healing at stationary contact. It's very well established that it happens. And the slip law does not. So that invalidates the slip law. But the slip law predicts the symmetry of up and down velocity jumps that the aging law does not reproduce well. And so basically, it's likely that both these formulations are wrong, but we don't have consensus about how to proceed. So anyway, we consider them as n numbers. So as I mentioned, what we want is a competition between different cooling
Simon,
mechanisms.
Simon.
Yes,
Yeah, someone. Yeah, Chen.
yeah. Go ahead,
Yeah.
because I can't see if somebody raised their hand. Yeah.
Yeah. So you just explained well for the aging law, if I understand it correctly. Because you combine different kinds of green growth, if I mean,
Yes.
mechanisms for the green side too. The blue part, basically, you allow the green side to grow following a Reynolds law. Maybe a different
Yes.
healing process can come in at different temperature, but it's a
Yes.
several process. You can add them all. Also, the weakening part is very similar to what like Smith's they call string weakening. Basically, if you times T here, the green reduction rate is proportional to the displacement or strain.
Yes.
If you
Correct.
divide by thickness. But this
Yeah.
is very similar to what we have dealt with calcite growth or green set reduction of calcite in those very similar framework. But as we are quite familiar with calcite, so when we are dealing this kind of green growth and reduction, green size growth and reduction, we confront a problem that is porosity. Probably you know those very classical work by the data site. People always cite for this green growth. I can't remember the names. They said, okay, they have compacting, no, sorry, they have healing the calcite with different composition and different different porosity, initial porosity and wet and dry, of course. They come across, so porosity and dry and wet conditions are extremely important. In other words, the numbers you put into the blue parts will very much depend on the porosity of the sample or your gouge. So
Yes.
so this kind of part might also play, because we know porosity also involves grain size change or during the velocity steps, for instance. How do you think of this factor? If wet or dry or porosity varies?
Yeah.
When?
Thank you for that comment. I think it's very important. So there is different ways of thinking about it. I imagine that in natural faults, the fluids are present and ubiquitous, and the pores are fully saturated with fluids, and so that should control very much the behavior of the system. And I have tried to avoid touching on fluids here, because even though there's a lot of experiments on permeability, porosity of gouge, there's not a lot of experiments that describe the effect of these fluids on strength and on friction, particularly. So there are some, but typically the papers are in dry or wet condition, or very low fluid pressure or very high fluid pressure. And there's only very few, I can count basically 2 papers that document gradual change of pore fluid pressure. So I think there's not enough laboratory experiments to really capture the role of fluids. And so I'm not in a situation where I feel comfortable putting some physics on it, because I'm not even sure what actually happens. So it doesn't mean that I don't think it's important. I'm just not ready to say anything about it. I'd like to see more experiments. Second is some people think porosity, the state variable of friction, is porosity. So it's a very different view of the physics, and it may be right. I'm not entirely sure. But some people believe that compaction and dilatancy modulate fault strength, and there's some merit in that. I propose a different explanation. I don't mean that the other is incorrect. Perhaps both are correct. But we would need to have more data to decide which one is the most realistic. And also, I'm not sure I know the papers you or the work you were referring to. So if you want to add a link to the chat, I can look at it later. I would appreciate that.
Good. Thanks.
Yeah, thanks. Okay. So so we have now even two evolution laws for the state variable of the size. And so the system is closed. We know how fast things flow, how fast things slide. We know the effect of temperature. We know how the size of contact junctions evolves over time and temperature. And as that happens, we can predict the real area of contact. So there's basically nothing else is needed at this point. Okay, and so I meant to say that I envision this as competing healing mechanisms, which means that for very finite ranges of temperature, really only one mechanism will dominate. And then another mechanism will dominate. And there will be a narrow range of temperature where both mechanisms are active. But that means they compete and one loses and one dominates. And so we can look at the system when only one mechanism dominates. So that kind of simplifies these equations a lot because the sum disappears when you have one term. And so we can find some closed form solutions. And at steady state, it looks like this. If only one mechanism dominates, the friction at steady state is simply a function of velocity, sliding velocity and temperature. So it's very simple. And so it's basically the velocity to a power, temperature to a power. And the sign of this power controls whether we have velocity strengthening, velocity neutral, velocity weakening, or temperature strengthening, temperature neutral, or temperature weakening at steady state. So this is controlled by a combination of parameters, particularly the power exponent P for the velocity dependence, and the difference of activation energy and enthalpy for the temperature dependence. And that's kind of important because you can be velocity weakening and temperature strengthening, and that may control the rupture style if you have crack-like or pulse-like ruptures, or super shear. But also you can be velocity strengthening and temperature weakening. And so Li-Feng actually worked on this. Any mechanism of weakening at steady state can create an instability. And so if you are velocity strengthening, you can still nucleate slow slip events, for example, as thermal instabilities. So the system predicts more weakening mechanisms that purely rate dependence. Okay, so to illustrate the behavior of this system, I consider a synthetic test where we have only two healing mechanisms, because that happens to be basically what is necessary to explain a lot of data, just two mechanisms. And so I give them different activation energies of 10 and 80 kilojoule per mole, and power law exponents such that we will have like typical frictional parameters. So with this choice of parameters, which I chose arbitrarily, we get a transition between low temperature and high temperature of velocity strengthening at low temperature to velocity weakening at high temperature. And this is characterized by the velocity dependence at steady state. So I simply measure that. And so we get these effective parameters A minus B of 4 10 to the minus 3 at low temperature and minus 4 10 to the minus 3 at high temperature. So explaining the transition velocity strengthening to beginning. And then the friction coefficient also evolves with temperature, the friction coefficient at steady state. And it is initially temperature weakening. So if you increase temperature, it will decrease the strength. It's temperature weakening. And then there's a change of mechanism, and so it transitions to temperature strengthening or temperature hardening. You can also implement this friction law in spring slider models that are driven by a constant loading of the system. And at room temperature, it will give you creep, and then that will transition gradually to stick-slip events of increasing stress drops. So illustrating the instability. And so this is a simple illustration, but it turns out to be very representative of many of the examples I shown in the introduction. So the second step is to compare the models and calibrate the model to infer the activation energies that explain different rocks in different laboratory experiments. So basically what I've done is look at all the experiments that I mentioned earlier and explore the best fitting parameters. What is the best activation energy, power exponent, reference friction coefficient, you name it, all of the parameters, try to calibrate them against data for the friction coefficient, A as a function of temperature, B as a function of temperature, the characteristic weakening distance as a function of temperature, and basically capture that. So I did that for many different rocks, and I'm only going to show it for one for the interest of time, for wet pyroxene. So these are experiments that were conducted and published fairly recently, probably from your institute with the work of Professor Hay. And these are data for augite, so it's wet pyroxene. And as you can see, these are experiments that are conducted between room temperature and almost 700 degrees Celsius, a wide range of temperature. There's no obvious trend of the direct effect parameter of temperature, so we explain this data with essentially the mean value, close to 8 or 9, 10 to the minus 3. However, there's a strong sensitivity to the A minus B, or B and A minus B are is a strong function of temperature. So in lab experiments of this type, these values are obtained through velocity jumps. But when the machine and the samples have a finite stiffness, it makes it difficult to, or non-unique, to find A and B individually. So typically A minus B is much better resolved because that's the steady state value. But A and B can covary, so that adds a little bit of noise. So if you look at the ratio of A over B, you can also eliminate some noise or some other things. And so looking at A, B, A minus B, A over B are different ways of looking at the same data that has some merit. And so this is done in these different quadrants here. So A and B are on the upper left, A minus B is on the upper right, and A divided by B is on the lower right. And another important measurement is the reference coefficient of friction at a given velocity. And that is also a function of temperature. So the error bars are the measurements from the lab, and the model is this continuous profile. So we can, in this case, look at A can be explained by power exponent of 120 plus or minus 40. It's essentially very large. And B, the model predicts that B is a function of A, and that's predicted by many models. It's also observed in the laboratory that A and B covary. And so we can explain B, A minus B, A over B with two mechanisms with different activation energies. One has 25 kilojoule per mole, the other is 45. And this is in wet condition, so it's compatible with these models, these deformation mechanisms in wet condition. That captures this deformation. If you ignore friction, you can explain A, B, and all this with different activation energies all the way to 70 kilojoule per mole. But if you consider the friction coefficient, then it eliminates the high range of activation energy because that overpredicts the frictional resistance. So in fact, at the end of the day, considering all the laboratory data systematically and consistently kind of narrows down these parameters quite well. So you can see in the lower plot here how using H2 equals 70 kilojoule per mole actually misfits the data quite significantly compared to using 45. And then Professor Hay was grateful enough to send me some the raw data that were used to make these measurements to calculate A, B, and A minus B. And these are shown here in black as a function of slip. And these are downstep velocity jumps. So we go from almost 1 micrometer per second to 0.1 micrometer per second. And this is done at different temperatures, right? 100 degrees, 200, all the way to 600. And you can see in the data itself, this transition from velocity strengthening at 100 degrees to velocity neutral at 200 degrees to slight velocity weakening at higher temperature. And again, this is slightly different from the theoretical, direct effect followed by the evolutionary phase because of the finite stiffness of the sample. So the response of the system is a little bit smoothed. So this is included in the model here by assuming a sample machine stiffness of 100 gigapascal per meter. So, and that's the same value for all of these experiments. And the model can reproduce these observations, these different, velocity dependence at steady state. So what's important here is that the physical model of friction, of rate, state, and temperature dependence predicts more data than an empirical model of rate and state with constant coefficient. You could fit this data, of course you can, with an empirical friction law, but you would have to change the constitutive parameters for every single experiment. Here, it's a single set of material properties that explain all of the curves, okay, all at once. So we are at a point, in this field where the physics of friction can explain more data systematically than the empirical one. So I think that's quite important. So there's two model predictions here, one with the aging law, one with the slip law. They use the same constitutive parameters except one for the weakening distance because, well, they behave slightly differently, but they have the same answer at steady state, so it doesn't matter. The second observation is that if an empirical friction law can fit this data, the physical one will fit it as well. So there's no caveat. We lose nothing in using the physical model, except we only gain something. We can explain the data with a single set of parameters. So then we can repeat this fitting exercise on different data sets. And those are the ones I introduced in the first half of the talk. And they're quite important because they basically cover a lot of different tectonic settings. We have granite for the continental crust, we have pyroxene for the oceanic lithosphere, we have hornblende in the subduction zone, we have shales in a sedimentary basin. They're important for various gate boundaries. And these are synthetic gouges. Okay, typically, well, except for the granite, but the minerals are selected. But then there's also natural gouge samples, particularly two that were selected from the longitudinal valley fault, and another from the Alpine fault in New Zealand from a drilling project. And so So it covers synthetic and natural gouge from many different tectonic environments that are relevant for natural seismicity. All of them show a transition from velocity strengthening to velocity weakening with increasing temperature. And then can all be explained by two healing mechanisms. Maybe more happen, but two is sufficient to fit the data. And the only difference is various activation energies. So overall, we find the activation energy for the direct effect between 10 and 50 kilojoule per mole, with power exponents between 55 and 150. And the activation energy for the healing mechanisms vary quite a lot. So for the dry sample of granite, it is in the range of 90 to 130 kilojoule per mole. And all the others are actually in wet conditions, because there's significant pore fluid pressure. And that brings the activation energy in a smaller range of 20 to 65 kilojoule per mole. So let me revisit that. First, the power exponents are between 55 and 150. So that's kind of interesting because if you're familiar with viscoelastic processes, the flow law that I use for the velocity is basically the same formulation as a viscoelastic flow that is used for, say, mantle convection and other things. But the parameters are completely different. If you do viscoelastic flow, the power exponent will be, say, typically it's between 1 and 5. So to be safe, viscoelastic flow could take place for power exponent between 1 and 20, maybe. But here for friction, even though it's the same mathematical expression, well, the terms inside don't mean the same thing. Traction is different from deviatoric stress, but it looks similar. But the power exponents are much higher, right? So between 55 and 150. So if you recall this yield criterion, it makes the velocity extremely sensitive to stress, right? It's all or nothing, essentially. So it's interesting because you can use a very similar mathematical formulation, but the power exponent, if you fit some data, can tell you if you're viscoelastic. So if you're less than 20 or less than 10, it's firmly viscoelastic. And if you're above 40, it's firmly frictional or plastic. So the formulation, the similarity of formulation should not misguide you to think that this is a viscoelastic flow or something like that. It's a kind of a coincidence that it looks the same. The parameters are very different, and the behavior is different. So what's interesting is that we find this dichotomy of, in dry condition, we have high activation energy, and in wet condition, we have low activation energy. It's very compatible with different mechanisms of deformation. And so we can basically summarize these findings in view of what we know about deformation mechanisms from different experiments. And so here I summarize different results. So at the very bottom of this plot, you have these vertical bars, and they are the different values found for the activation energy of the direct effect, so Q, and that's basically lower than 50 kilojoule per mole. And above you have the range of activation energies for different mechanisms: subcritical crack growth, pressure solution creep, crack healing, viscoelastic collapse. And I added the activation energy for healing H1 and H2. So there's two healing mechanisms to fit the data on top of that. So we can directly compare. And so for dry granite, H1 and H2 are around 100 kilojoule per mole. So that's very compatible with viscoelastic collapse of the various minerals that form granite, mica, quartz, feldspars. And all the others are much lower, between say 20 and 70 kilojoule per mole. And they are all compatible with all the other different mechanisms. It can be crack healing, it can be pressure solution creep, it can be subcritical crack growth, all being possible because of the presence of water. The direct effect activation energy Q is quite low. For example, for shale, it's 10 kilojoule per mole. There's not a lot of processes that are well identified that have such a low activation energy. So my interpretation is that it's an effective value that includes some athermal processes that are not thermally activated. These are basically transport mechanisms. So when you move something from A to B, it's not thermally activated. So granular flow is one such thing, where if you slide by rolling the grains, this is not a chemical reaction. This does not change the configuration, and so it has an effectively zero activation energy. So that means that granular flow is also active in fault gouge and participates in the sliding. Well, that's my interpretation at least. And the others may include some subcritical crack growth, maybe with stress corrosion because fluids are present, pressure solution and precipitation, crack sealing, crack healing, cementation, etc. So I think there's a good correspondence between the activation energies that are found to fit the mechanical data with completely independent experiments that constrain activation energies of specific mechanisms. So this brings me to my conclusion that we can derive a physical model of rate, state, and temperature dependence friction, dependent friction, based on the real area of contact. So it explains mechanical data, but it also explains the area of contact, which is otherwise not explained in empirical friction laws. And so we can then explain and constrain the thermodynamics of friction for many different rocks that are representative of many different types of plate boundaries. That constrains pore exponents in 55 and 150, activation energy for direct effects, and also different activation energies for healing. And that is likely to be due to the activation of different mechanisms, but also the same mechanism for different minerals. So I want to emphasize that the model is far from complete. Again, I mentioned these strong weakening mechanisms that happen at high slip speed that is completely ignored in this model. There's also other effects. The empirical frictional properties depend on sliding velocity, actually, so I haven't discussed that. And there's dependence on normal stress and perhaps even more importantly on, like we discussed earlier, on pore fluid pressure, right? So there's not only a thermal activation, but there is a hydrothermal activation. So there's still a lot of work to be done to capture the physics of friction, but I think what I've proposed is a framework, a starting point where we can build on and improve the model when more data become available to make more realistic predictions. And the goal in the end is to make strong connections between mechanics and chemistry and phase transitions and continue towards a physics-based model of friction.